Hello, this is the final part on zero-sum games. So what have we seen so far? In the first part, we introduced this notion of zero-sum games and the notion of pure strategies, and we showed that max-min is less than or equal to min-max always, and equality is attained in games where there are saddle points. Okay, this was pure strategies. And in the last video, in part 2, we introduced this notion of mixed strategies, and we wanted max-min and min-max over mixed strategies. So we saw that computing max-min can be done by a linear program. So we gave an LP to compute max-min over mixed strategies. So what we will see today is that we will prove that over mixed strategies, we will always have max-min equals min-max. Okay, quite contrary to the pure strategy case. Okay, let's see this. So let's first recall the LP for max-min. So for this rock, paper, scissors game, so how did we write LP for max-min? Now you assume that the mixed strategy of max place x1, x2 and x3, okay, and the cost is x0, say. Okay, now to write the LP, you look at each pure strategy of the minimizer. So let's start with the first pure strategy, which is playing this column. Now, if max plays this mixed strategy and min plays this pure strategy, the payoff would be x1 times this thing plus x2 times this plus x3 times this. That is what is written here. x1 times 0 plus x2 times 1 and x3 times minus 1. Okay, so if min plays this, the cost is this. And remember that we are computing max min. So min can ensure that the cost is at most this value. Okay, so that is why we have written that the cost is at most this. Okay, now when min plays this, min can ensure that the cost is at most minus 1 times x1 plus 0 times x2 plus 1 times x3. So that's what is coming here, minus 1 times x1, 0 x2, 1 x3. And similarly, when min plays this, the cost will be the corresponding payoff. Okay, it is at most x1 1, x2 minus 1 and x3 0. Okay, and in addition, we have to give a constraint on x1, x2, x3, which is the fact that it's a probability distribution. So x1 plus x2 plus x3 equals 1, and each of them is bigger than or equal to 0. Now on the same lines, we can try to write an LP for min-max. So to write the LP for min-max, we have to look at a mixed strategy y1, y2, y3 for min. Okay, and then we have to enumerate over all pure strategies of max. Okay, so and let me assume that the cost here is y0, why not? Now when so this is the mixed strategy of minimizer. Now when maximizer plays the pure strategy rock, the payoff would be 0 times y1 minus 1 times y2 plus 1 times y3. That is here on the left hand side. Now when max plays rock, he can ensure at least this much. Okay, so hence the min-max value, which is this, is at least this. Okay, so recall that this is you can think of this as the fixed strategy for min, and max is playing various strategies, and when max plays this, max can ensure at least this thing. So y0 is at least this. Similarly, y0, when max plays this, the cost would be y1 times 1 plus 0 times y2 plus y3 times minus 1, and y0 is at least this. And finally, when max plays this, minus 1 y1 plus 1 y2 plus 0 y3, so this min max is at least this. Okay, and then we vary over all strategies of min, which gives us these two things. Okay, now these are the two LPs, LP for max min and LP for min max. Okay, now let's do an exercise. So we start with the LP for max min, which is this thing, and let's try to write the dual of it. Okay, now to write the dual, let's assume that we multiply these. There are 4 constraints here. We multiply this one with y1, y2, y3 and y0. Okay, now so in order to write the dual, what should we do? We should first look at the coefficient of, the thing is, these are written on the right hand side, but these are all variables. So the LP is actually x0 minus 0x1 minus 1x2 plus 1x3 is less than or equal to 0. So all these should be here. Okay, so now let us look at the coefficient of x0. Coefficient of x0 is y1 plus y2 plus y3. Okay, and then in the cost it is 1. Okay, so here it is y1 plus y2 plus y3, and here it is 1. Now why have I put an equality? Because x0 is unrestricted here, right? So the corresponding equation for x0 should have an equality. Okay, now let's look at the coefficient of x1. So that is, if I move it here, this is 0 times y1 plus 1 times y2 minus 1 times y3. So that comes here, and here there is an x1 and there is plus y0. Now here there is no coefficient of, in the cost, the coefficient of x1 is 0. So 0 comes on the right hand side. And now why there is a bigger than or equal to? Because x1 is bigger than or equal to 0. So you remember the dual, when we did ax less than or equal to b, x bigger than or equal to 0, you had correspondingly A transpose y bigger than or equal to c and y bigger than or equal to 0. So here you will have a bigger than or equal to. Similarly, you write the coefficient of x2, that will be minus 1 y1 plus 0 y2 plus 1 y3 plus y0 bigger than or equal to 0. Similarly, you write for y3. Now why should I add y1, y2, y3 bigger than or equal to 0? Because these are all inequalities. Okay, so for these inequalities, to maintain the relation in the dual, we need bigger than or equal to 0 here. Okay, so this is the standard dual, and as you see, it turns out that this is exactly the LP for min max. Okay, so what we wrote here is just obtained in a rearranged form. Okay, so this is the first step. Now the next thing to note is that, see, the primal has a feasible solution. You can always put x1 to be 1, x2 0, x3 0. You can always play a pure strategy, okay, and then get some value. So the primal is feasible and also bounded, because the set of feasible solutions is contained inside the hypercube of the corresponding dimension. Okay, so the primal is bounded and feasible, hence there is an optimum, and this implies that the primal optimum will be equal to the dual optimum based on whatever we know so far, and hence, at least in this example, we have seen that max min is equal to min max. Okay, so this is the main thing. In general, if we are given a game, if we write the LP for max min and min max, we will see that they are duals of each other. Okay, so in general, how would you write the max min LP? So let me go through that. so of course this is maximize x0. Here you have to go through every pure strategy of the minimizer. That means you have to look at every column. Okay, so that's why you have m1. So the first column will have m11, m21 till mm1. So that's why m11x1 plus m21x2 till mm1xm. And minimizer can ensure that the max min is at most this. Now the same thing we wrote for the second column till the nth column, and then this is the fact that we are ranging over all mixed strategies of max. Now to write the min max LP, you will look at the pure strategies of the maximizer. So this one would be m11, m12 till m1n. So that's what is coming here. So after fixing y1, y2, yn, and max can ensure that the min max is at least this. So we have y0 is bigger than this, y0 is bigger than the second row, the equation coming from the second row, and so on till the m rows. And this one is just ranging over all mixed strategies of the minimizer. And if you take the dual, you will see that you will get these two are primal dual pairs. Okay, and this is the famous min-max theorem, minimax theorem in zero-sum games. The fact that max-min equals min-max over mixed strategies. And the feasible solutions of the primal and dual give mixed strategies x and y such that y is the best response to x and x is the best response to y. That is, if max plays x, the min over all strategies of minimizer will give you a value, and that value is attained by this y bar. Okay, so y bar is the best strategy if min knows that max is playing x. Now similarly, if max knows that min is playing y, then the best response would be x bar. Okay, so first of all, there is no reason max should not play x bar, because if min plays y bar, then it's best for him to play x bar. Okay, now again, there is no reason why min should not play y bar, because if max plays x bar, then the best response is y bar. Okay, and since we know that the max min is achieved at x bar and the min max is achieved at y bar, so both players play these corresponding strategies. So this is a Nash equilibrium over mixed strategies. So there is no incentive for each player to deviate, and these x bars and y bars are the optimal solutions of these two LPs. Okay, so mainly we want to say that max min is equal to min max over mixed strategies, and for this we have extensively used what we know about LP duality. Okay, this finishes the part on zero-sum games.